So guys, good afternoon. My name is Perfetta. I'm from VIT. So in the previous class, we have seen that how to find the transfer function for electrical system or electrical modeling system. So we have seen that how to find the transfer function from the given electrical circuits. That means maybe the RLC circuits or it may be RC circuits. So we have seen that how to find the transfer function for the given circuits. Okay, I hope you understood some concept on that. So, and I have told for you that if you have any doubts or any suggestion, any comment, you can give me feedback to me at the comments of the video after watching all my video. So, and I'm ready to help you. Okay. So today we are going to see the news topic, which is the new topic of this control system, which is known as the mechanical system elements. So as we know, there are so many types of the systems, and we have seen the electrical system or the modeling of the electrical system or electrical system modeling. Today we are going to see the mechanical system elements. So here when we say the mechanical system elements, these system elements are due to the mechanical or the mechanical due to some movement, or when we say the mechanical, there is some the physicality or the movement. Okay, so there are basically there are three basic mechanical elements. They are the basic components or the elements for the mechanical system. The first one is the spring, which is called the elastic element, and the second one is called the damper, which is the frictional element, and the third one is known as the mass, which is the inertia elements. So as we know, the inertia is it's the law which is the law of the Newton second law. Okay, the Newton second law says that inertia is equal to mass time acceleration, or the law of the inertia, or which is called say that the force applied is equal to mass time acceleration, right? So here also this concept is also coming here, because mass is the dealing with the law of inertia. Okay, so for that reason we are saying that mass is the related with the inertia element. When we say translational and rotational versions, these are the passive or it's non-energy producing. When we say passive, they can't produce energy, but they are the users of the energy device. So the basic three elements are known as passive element devices, or the non-energy producing devices. So driving inputs, force and the motion sources which cause the elements to respond. Each of the elements has one of two possible energy behaviors. Okay, each of the elements has one of two possible energy behaviors. store all the energy supplied to it and dissipates all the energy into heat by some kinds of friction effect. So all the this all the that means all the elements the above, and that means the first one is mass, spring, and damper. This all have the only two behaviors. One is storing energy, and the second is dissipating of all energy. So when we see one by one, when we say spring, which stores energy in the form of the potential, and when we say mass, stores energy as a kinetic energy, or it stores energy as kinetic. When we say potential and the kinetic, the potential energy, the energy which deals or due to position, no any movement, or it's the stored energy. When we say the kinetic energy, the energy which is due to motion, okay? So we can say that the potential energy is equal to mgh. M is nothing but the mass of the object, and g is the gravity of the element, and h is the height of the objects or the body. So here spring stores as a potential energy as a potential energy, and the mass stores energy as a kinetic energy. So we can say the kinetic energy is equal to half by mv squared. So this is due to the motion. So so we can say that spring stores energy as the potential energy that is due to position, no any movement, whereas the mass stores energy as the kinetic energy, which is due to motion. So damper dissipates energy, okay? No any storage of element in damper, but it dissipates energy. So the other thing is dynamic response of each element is important, okay? The dynamic response. Dynamic means nothing but variable, not constant. It is changeable. We can say like this. So the dynamic response of each element is very important here, okay? When we say dynamic, there are two responses. Dynamic response means either the step response or the frequency response. Or so now we are going to see the all elements one by one. So the first element is the spring element. So when we say spring element, it is the real world design situation. Okay, real world spring is neither poor or ideal. So here, real world spring has inertia and friction. So pure spring has only elasticity. It is the mathematical model, but not a real device. Okay, you have to assume like this. So some dynamic operation requires that spring inertia and or damping not be neglected. Okay, so here when we say the ideal spring has the property or the behavior of the linear, and the nonlinear behavior may often be preferable and give significant performance advantages. Okay, so the device can be pure without being ideal. The example for this is the nonlinear spring with no inertia or damping. So nonlinear spring without any inertia or damping can be pure without any being ideal. Okay, so device can be ideal without being pure. Example for this, without being pure. Example for this, the device which exhibits both linear springiness and linear damping. So you have to assume or understand these things. So pure and ideal spring elements. The pure and ideal spring elements. So we can see this the formulas here. This is F is equal to, F is nothing but force, and T is nothing but the time period. Okay, here F is equal to Ks into x1 minus x2, which is equal to, we can say that Ks of x, Ks of x. So F is equal to Ks of x, and T is equal to Ks into theta 1 minus theta 2 into Ks of theta. So here, when we see here, this T is not theta, sorry, T is a tau, which means the torque, and this F is the force. So here we are seeing that in the case of translational and angular or rotational. Okay, the second one is rotational because this is the angular displacement, and the first x1 minus x2 is the linear displacement. So we can say that F is equal to Ks of x. K is nothing but spring stiffness. Okay, spring stiffness. So like this we can say the formulas. So Ks is nothing but the spring stiffness, which is SI unit is nothing but Newton per meter, and or we can say that Newton meter time per rad. Okay, so here x is equal to Cs of F. Cs is nothing but the compliance or the softness parameter. So theta is equal to Cs by T, capital T. So 1 by Ks is equal to Cs. Cs is nothing but compliance or the softness parameter. So this is the diagram for Ks and the Cs. So in the case of Ks, the X is input and F is output. In the case of Cs, F is input and X is output. Okay, Ks is nothing but the spring stiffness. This is the compliance or softness parameter. So we can say like this. And the other thing is the energy stored in spring is equal to Es is equal to C2F square over 2, or K2X square over 2, we can say like this. So when we say dynamic response, it is the zero of the dynamic system model. So when we say dynamic, there are two responses. When we say dynamic response, we have two responses. The first one is the state response, and the second one is the frequency response. Okay, when we say the real springs will not behave exactly like the pure or the ideal element, so one of the best ways to measure this deviation is through the frequency response. To measure this deviation, that means the real springs can be measured or done by using the frequency responses. So in another way, we are going to see the spring element. Spring element. So in the case of the spring element, the differential work done can be calculated as F dx. Okay, F into dx, which is equal to Ks of x into dx. So total work done is the differential work done and total work done. So we have seen that the differential work done is calculated as f dx or ks into x into dx, but the total work done can be calculated as integration of 0 into x naught into ks of x dx, which is equal to ks x naught square over 2, which is equal to csf is f naught square over 2. This is the total work done. So these are the figures for the linearity of this spring element. This spring element has the graph which has linear. That means x is in the x-axis time and the y-axis force. So there is a deflection on the y-axis, and this is what we can say the pure or ideal spring element. So this is the sometimes some which is known as the real spring. So it has some linearity. Okay. So this is the graph for spring elements of the linearity. So the other thing is the frequency response of the spring element. So when we say the frequency response, it's one of the response or the dynamic response. So here we can say that f is equal to f naught into sine of omega t, and x is equal to cs f naught sine of omega t. So this is the frequency response of the spring element. The frequency response of the spring element will be like this, and the amplitude also should be f naught into fb of f square into af. This is the amplitude. The amplitude in the case of cs and the amplitude in the case of af. So like this we can calculate. And the other thing is this is the frequency response graph. Okay, for spring element. So well, now what we are going to see is zero order dynamic system model. So here in the zero order, this is the q naught is equal to kqi. Like this we can calculate, and the graph should be like this linear graph or some constant graph or the straight graph. So like this we can see, but the first graph is showing that the step response, and this is the second graph showing that the frequency response, but this is the step response. The first is the step response, whereas the second graph is known as the frequency response. Both graphs are for zero order dynamic system model. Okay, yeah. The other is the more realistic lumped parameter model for a spring. Here we can say this is the diagram for lumped parameter model for a spring as a lumped form. Okay, as a lumped parameter. So we can represent it like this. This is the dashboard, or which is known as a damper. B is represented, or FV or B is represented as a damper or dashboard, and this is KS is nothing but the spring, and this is mass, the given mass. So like this we can represent as a two loops. There are two loops here. This is the input and the input. Like this we can get the diagram for the lumped parameter model for spring. Okay. The other thing is non-linearity for non-linear springs. Okay, or we can say that linearization for non-linear. Okay, here we have the formulas like this, and we have the graph. That means we have the diagram like this for nonlinear spring. Here, this is the weight of the object or the mass, which is weight. This is the spring we have. Some forces applied or gravity, or like this we can represent, and this is non-linear, not linear. Okay, like this. So here we have the formula y is equal to f of x naught plus df by dx at x is equal to x naught, and the times x minus x naught plus d square f over dx square at x is equal to x naught into x minus x naught square over 2 factorial. It's continuous like this up to so many factorials. So we can say that y is equal to y naught plus df by dx into at x is equal to x naught into x minus x naught. So we can say that y minus y naught is equal to plus df by dx at x is equal to x naught into x minus x naught. So y is equal to y cap is equal to kx cap. So like this we can do, and the other thing is the real spring. In the real spring, nonlinearity or non-linearity of the force or the deflection curve. So in the real spring there is non-linearity and non-coincidence of the loading and unloading curves. So non-coincidence of the loading and the unloading curves is nothing but it is the second law of the thermodynamics. Okay, that guarantees that the area under the loading FVSX, according to this graph, FVSX, x curve must be greater than that under the loading FVS x curve. It is impossible to recover 100% of the energy put into any system. This is the graph for the real spring. Yeah. So now we are going to see the several types of the practical springs. So we have the coil spring, and we have hydraulic or the oil spring, and we have the cantilever beam spring, and this is the pneumatic or the air spring, and the clamped in the beam spring, ring spring, rubber spring, or the shock mount. Okay, the tension rod spring and the torsion bar spring. So this or you can see these types of the springs from this graph also. Okay, so what we are going to see the spring-like effects in unfamiliar forms. Okay, so as we have seen, these are the several types of the practical springs. Here, these names are given according to the function or the use at where we are using, and according to the application, these names are given to them. Or same thing is happening here also. So spring-like effects in unfamiliar forms. So there are some types of springs also here. So aerodynamic spring, gravity spring, or the pendulum. Okay. So gravity spring or the liquid column. Okay. There are two springs in the gravity case, the pendulum and the liquid column. So the buoyantic spring and magnetic spring, electrostatic spring, and the centrifugal spring. So we can see from this picture also. So here we are giving these names according to where these springs are applied in the daily life or real life application. Okay, so this is all about the spring elements. So now we are going to see the damper element. As we have seen at the beginning of this class, so there are three types of the components or the elements for the mechanical system. The first one is the spring element. The second one is the damper element. The third one is the mass element. Okay, so we have seen the spring element. The spring element, which is known by storing energy as the potential energy or the stored energy. The potential energy is nothing but the energy due to position, not any motion. Okay, so here when we say the mass element can store energy as what? As the kinetic energy, that means due to motion. So now we are going to see the damper element. So as I said for you, the damper element is not storage element. Okay, or it can't store energy, but it dissipates energy. So dissipates energy, all the energy supplied to it is dissipated, not stored. Okay, so that means it converts the mechanical energy to what? To the thermal energy. So that means the damper element which changes what? The mechanical energy into the thermal energy. Okay, yeah. So it's dissipator of energy. Okay, so various physical mechanisms usually associated with some form of the friction can provide this dissipative action of the damper. So this is the friction element. This damper is the friction element. Whereas the mass is which element? So mass is the inertia element, and that is the what about this the damper element. So here the various physical mechanisms usually associated with some form of the friction can provide this displaced action. So example, the column which is the derived friction or damping. So material, for example, the other is material damping, which is the solid damping, the viscous damping, like this we are seeing. We can see these types of the damper elements. So the pure or the ideal damper element provides the viscous friction. So all mechanical elements are defined in terms of their force, motion relation. So electrical elements are defined in terms of their voltage or current relations. Or so pure or ideal damper force or the torque is directly proportional to the relative velocity of it is to in this. So the damper force or the torque is directly proportional to what? To the relative velocity. So that means when the force or the torque increases, the velocity also increases. So this is known as the direct proportional. This is the relation between the damper force or the torque and the velocity. In case of the damper element is the direct relationship. Okay, so we can represent that the formula for this F is equal to B into dx1 over dt minus dx2 by dt, which is equal to B times dx by dt. Here also is for F, and for this for capital T. For capital T, B into d theta 1 over dt minus d theta 2 over dt, which is equal to d theta over dt. Okay, yeah, like this we can get. And so this in the first case, this is the force and this is the torque. Okay, torque is nothing but it is due to the rotational. This is due to the transitional or the linear. Okay, so we can identify or differentiate these concepts like this. Force or torques on the two ends of the damper are exactly equal and opposite at all times, just like what? Just like a spring. So pull springs and dampers have no mass or inertia. The pull springs and dampers have no any inertia. Okay, no any inertia in the case of the pure springs and dampers. There is no mass or inertia in the case of pure springs and dampers. So this is not true for real springs and dampers, but it is true for what? For the pure springs. This is not true for a real springs, not. But for pure springs, there is no any mass or for pure spring or for dampers. There is no any mass. There is no any mass or inertia, but it is not true for the real springs and dampers. Okay, so units for B, that means for damper, to preserve the physical meaning, which is Newton by meter per second. Okay, Newton by meter per rad per second. This is the unit for B, which is nothing but the damper, or we can represent as FV also. Small FV also can represent the damper, and the other is also B is also same, but the unit for this is Newton per meter per second, and Newton meter per rad per second. Like this, we can say the units for these types of element. Okay, so the transfer function, for the transfer function, differential operator or notation is used. So dx is equal to, for the dx is equal to what? There is some delta, so dx by dt, and x by d is equal to, and there is delta, and integration of x into dt, and d square x is equal to d square x, capital D square x is equal to small d square x over dt square, and x by capital D square is equal to the delta of integration of double integration of x dt into dt at dt. So like this we can calculate the transfer function. So the operational transfer function, so f is equal to b dx. B is nothing but dash spot, and theta tau is equal to, or torque is equal to b dq. So like this we can say. So at the f is equal to b dx, we can say that f by x into d, which is equal to at the delta of bd, which so we can say that t by theta into d, which is equal to as the delta of bd. So x by f as a for t is equal to b dq, and x by f into d is equal to as the delta of I by 1 by bd. That means theta by t into d is equal to as the delta of 1 by bd. So we assume the initial conditions are 0. So we can say that the initial conditions are 0 here. So damper element dissipates into heat all the mechanical energy supplied to it. Okay, so the power is equal to force time velocity. There is a delta at the equal sign. So we can say that power is equal to force time is equal to as the delta of force time velocity, which is equal to f into dx by dt, which is equal to dash spot into dx by dt square. So force applied to damper causes a velocity in same direction. So the force applied to damper causes for the damper causes, it's the velocity in the same direction. The power input to the device is the positive, since the force and the velocity have the same sign. Okay, so it is impossible for the applied force and the resulting velocity to have the opposite sign here. So thus a damper can never supply power to another device. That means the power is always positive. So here the spring absorbs this power and it stores energy as a force is applied to it. But if the force is gradually relaxed back to zero, the external force and the velocity now have the opposite sign, showing that the spring is what? Driving power. So the total energy in the case of the damper is, that means, the total energy dissipated in the case of the total energy dissipated is in the case of the damper is integration of P dt is equal to integration of B into dx by dt square dt, which is equal to integration of B into dx by dt ds, which is equal to integration of f dx. So this is all about the damper element also. So here we can see this the graphs or this the representations for damper element. So step input force causes instantly, which means that a pure damper has no inertia. A step of dx by dt and a ramp of x. So like this we can do it. So frequency response of damper elements, which is equal to f is equal to f naught sine into omega t. That means b dx of dt. That means x minus x naught is equal to 1 by the dash spot of the integration of 0 up to 1 f naught sine of omega t dt. Okay, this is nothing but the frequency response for the damper element. So we have seen for the spring element also. So here this is the frequency response for the damper element. Okay, so x minus x naught is equal to 1 by b. B means nothing but the dash spot or damper. So into integration of 0 up to 1. That means the integral elements or the interval for integration is 0 up to 1. Okay, into f naught sine of omega t dt. Okay, so this is equal to f naught by b omega into 1 by cos of omega t. So here we can say that x by af is equal to f naught b omega over f naught, which is equal to we can cancel f naught by f naught. Only the left thing is 1 by omega b omega. Okay. So now we are going to see the sinusoidal transfer function. In the case of damper element, we have sinusoidal transfer function. So x by f into d is equal to 1 by bd. So which implies that d is equal to I omega, which implies that x by f into I omega is equal to 1 by omega b, which is equal to m is less than 5. Okay, so here m is the amplitude ratio of the output over input, and this is phi here, and phi means here the above phi is the phase shift of the output since with respect to the input sine wave, or positive if the output leads the input, and negative if the output lags the input. Okay, so here we can mathematically we can represent this the sinusoidal transfer function as x by f into I omega is equal to 1 by I omega into b, which is equal to m less than phi. M is nothing but the amplitude ratio of the output over input, and which is equal to less than phi. Phi means nothing but the phase shift of the output sine wave. So, which is equal to 1 by b omega less than minus 90 degree. So here m is equal to 1 by b omega, and the phase shift is that means phi is equal to phi or psi is equal to minus 90 degree. Okay, so the other is nothing but the real dampers. So a damper element is used to model device designed into a system. So the example for the real dampers are the automatic shock absorbers, okay, or for unavoidable parasite effects. Example for this is air drag. So to be an energy dissipating effect, a device must exert a force opposed to the velocity. If the device exerts force opposed to the velocity, we can say that that device is energy dissipating device. Okay, or it has the energy dissipating effect. We can say like this. So here. Power is always negative when the force and the velocity have opposite direction. When the force and the velocity have the opposite direction, power has what? Positive or negative? Which has negative. Okay. So let's consider examples of real and tensional dampers. When we see this, that means the viscous piston or cylinder damper. This is mu. Mu is equal to fluid viscosity. Fluid viscosity. Here we can say that mu is equal to fluid viscosity, and a relative velocity between the cylinder and the piston forces the viscous oil through the clearance space H. Okay, which means the shearing the fluid and the creating a damping force. So here B is nothing but dash spot, which means dash spot, which means which is a damper element. So which is equal to 6 pi mu L over H cube into R2 minus H by 2 square minus R1 square into R2 square minus R1 square over R2 minus H over 2 in minus H. So here we can see that simple shear damper and viscous viscosity definition. So when we see the formula for this, F is equal to 2a mu by T into V. Here B is equal to F by V over 2a mu over T. So mu is nothing but the fluid velocity, and delta is the shearing stress over delta is equal to the shearing stress over velocity gradient, which is equal to F by A over V by T. So this is the example for shear damper or viscosity definition or a simple shear damper. So this is a diagram, or you can see like this also. So examples of the rotary dampers. So examples for the rotary dampers. So here we can see like this also. Yeah, this is the damping effect. The damping effect are assumed to be confined to the gaps of width T. So like this we can see this diagram. And so B is equal to pi this Q L mu over 40. You can say like that. B is equal to like this also. Here we can see that the commercial air damper, and yeah, like this we can see also. And this is the diagram. Yeah, like this also we can see, and like this also we can see air damper. When we say when we see the commercial air damper, this is the diagram. This is the Pyrex glass cylinder. This is the graphite piston, and this is the turbulent flow or non-linear damping. This is the needle valve, or this is the what? Damping adjacent. Okay, this is the parts for this commercial air damper, and this is F and V. This is damper element. Like this we can see, and this is data taken. The data taken by using the equations or like that. So air damper, much lower viscosity. There is for air damper, it has much lower viscosity and less temperature dependent, and it is no leakage or sealing problem. So this is according to the air damper. And the other thing is motion of the conducting cap in the magnetic field generates a voltage in the cap. So this current is generated in the cap's circular path. This we are talking about this the eddy current damper. Yeah, eddy current damper. In the eddy current, motion of the conducting cap in the magnetic field generates a voltage in the cap. So a current is generated in the cap's circular path, and a current carrying conductor in a magnetic field experience a force proportional to the current. So the result is a force proportional to and opposite the velocity. So the dissipated energy shows up as I square R, heating of the car. So like this we can see the diagram also like this. This is chopper car, and this is the damper element. This is D diameter. This is the permanent magnet. This is the cross section of the circular configuration. So this is the concept for the eddy current damper, and here we can see that the damper. So the temperature sensitivity or the damping method. This is the temperature sensitivity. So there are. This is the X and the Y graph. In the Y graph, there is the temperature effect on damping, and in the X graph, there is the room temperature. In the room temperature is in the degree Fahrenheit. So like this, we can see the eddy current also forming in this place. This is the air conduction. This is eddy current. This is the siliceous oil, and this is petroleum oil. Like this, we can see the diagram or the graph for the damping methods of the temperature sensitivity of the damping method. So in the same way, we have seen the eddy current concept. So other examples for damper performance like this we can see. And the other thing is the damper element can also be used to represent unavoidable parasitic energy dissipation effects in mechanical system. So the frictional effects in moving parts of machines. So fluid drag on vessels, or for example cars, ships, aircrafts, and etc. There are the examples for vehicles. So cars in the ships and aircrafts, the fluid drag. So they are using the what damper element, or this damper element forms. So the windage windage losses of the rotors in machines. So the high stress losses associated with the cyclic stress in materials. The structural damping is to derivative joints or welds. It's it. So air damping of the vibrating structural shapes. These are all where we are using the damper elements. So the other thing is the hydraulic motor friction. So and its component. This is the some the graph types or what kinds of graphs we are getting. This is the hydraulic motor friction and its component. So the other thing is the column friction. That means the modeling and the simulation for the column friction. So in most control system, column friction is that means nuisance. That means column friction is difficult to model and troublesome to deal with in the control system design. So it is a nonlinear phenomenon in which a force is produced that tends to oppose the motion of the bodies in contact in the mechanical system. So undesirable effects, which means the hang-off and the limit cycling. So hang-off means nothing but or it's a DC limit or a DC limit cycle. So DC means direct current limit cycle. So prevent the steady state error from becoming zero with the step command input. So limiting cycling is a behavior in which the steady state error oscillates or hunts absolute zero. So what should the control engineer do in this case? So what should the control engineer do? So the control engineer can do the following tasks. That means minimize the friction as much as possible in the design. So it's afraid it can that means the control engineer can appraise the effects of the friction in a proposed control system design by using the simulation. Okay, if the simulation predicts that the effect of the friction is unacceptable, you must do something about it. So here remedies can include simply modifying the design parameters. That means gains using the integral control action or using more complex measures such as estimating the friction and the cancelling its effect. So modeling and the simulation of friction should contribute significantly to improving the performance of the motion control system. So this is the modeling, the graph or the graphical representation for the modeling Columbus friction. Here F1 we have, this is F stick, F stick we can say like this, and this is V. V is nothing but the velocity. This is the stiction or the column friction model. So here the case study to evaluate the friction model. This is the V naught, this is V, and this is the spring, this is the mass, and this is the force applied. So for example, if the mass is given is equal to 0.1 kilogram and the K is equal to, K is nothing but the spring given is 100 Newton per meter, and F stick is equal to 0.25 Newton, and F slip is equal to 0.20 Newton. So here in F slip we are assuming that independent of velocity. So V naught is equal to a step of 0.02 meter per second at t is equal to 0 second. So here the friction model in simulate, this is in the simulink. So we can represent like this. This is the resultant force and in the first place, and it's at input into the resultant force friction force. This is the friction force also. And here in the two from the reset integrator. So from reset integrator we are coming to the velocity. Velocity is entering into the reset integrator or velocity. So to reset integrator also like this. The friction model like this we are doing. This is the friction model in Simulink. Okay, the Simulink block diagram. This is the Simulink block diagram. We can see like this also. This is the diagram for the Simulink block diagram. Here, the example with the friction model. This is the diagram also, and this is also diagram, and this is also this is the Coulomb friction example, and this is the position velocity friction force with time like this. Here, when we see this graph, at the x-axis there is time, which means the period, and in the y-axis there is the what is there? Position velocity friction force. Okay, so the inertia elements. So inertia elements. We are going to see the inertia element, which is nothing but the mass which stores energy in the case of the kinetic, which is due to the motion. Okay, it's designer rarely inserts a component for the purpose of adding inertia. The mass or the inertia elements often represent undesirable effect, so which is unavoidable since all the materials have mass. So here what we are seeing is there are some applications in which mass itself serves a useful function. Example, the accelerometers and flywheels are an example for this application. So accelerometer useful applications of inertia. So these are the applications, accelerometer. Flywheel are used as energy storage devices or as a means of smoothing out speed fluctuations, the speed fluctuations in engines or other machines. Okay, so these are also the diagrams. So Newton's law defines the behavior of the mass element and refers basically to an idealized point mass. So here the summation of force is equal to mass time acceleration. This is nothing but the Newton's second law of motion. This is the law of the inertia. So in the inertia element, we are using the concept of the Newton's second law. Okay, this which said that the summation of the force is equal to mass time acceleration. The concept of rigid body is introduced to deal with practical simulations. For pure translatory motion, every point in a rigid body has identical motion. Okay, real physical bodies never display ideal rigid behavior when being accelerated. So we can say that the real physical bodies cannot display ideal rigid behavior when being acceleration, or if there is acceleration, the real physical bodies never display ideal rigid behavior. So the pure or the ideal inertia element is a model, not a real object. It's a model only. Okay. So this is the nothing but this is the diagram. So yeah, we can see like this also. Yeah, we can see like this also. Newton's law in rotational for bodies undergoes pure rotational motion about a single field axis. That means this is according to summation of torque is equal to moment of inertia into angular acceleration. This is according to the rotational. Okay, but on the rotational mechanical, but the first one is according to the translational, or it's in the case of the linear. Okay, so same concept, but only the change of the rotational and translation only. So the concept of moment of inertia J also considers the rotating body to be perfectly rigid. Note that to completely describe the inertial properties of any rigid body requires the specification of one, its total mass, the second, location of the center of mass, and the three moments of inertia and the three products of inertia. So the rotational inertia is have the SI unit, which is joule or kilogram per meter square. Joule times kilogram per meter square. So here the tangential force, which is equal to mass time acceleration, which is equal to 2 pi RLP R rho into dr time r alpha. This is the rotational type. The total torque is equal to integration of 0 up to r into 2 pi rho L alpha r cube dr is equal to pi r square L rho over r square over r, which is equal to m r square over 2 into alpha, which is equal to j alpha. Here rho is equal to the density, L is length, alpha is angular acceleration, r is radius, t is torque, and that is, we can say m is the mass, yeah, j is nothing but j alpha. So here moments of the inertia for some Coulomb shapes like this, you can see. How do we determine J for complex shapes with possible different materials involved? So in the design stage, where the actual part exists only on paper, estimate as well as possible. Once a part has been constructed, use experimental methods for measuring inertial properties. How? When you say how, you can do like this, the experimental measurement of the moment of inertia. So the summation of torque is equal to J alpha, which is equal to J into alpha means nothing but d square by theta over dt square. This is the nothing but the second derivation of the angular displacement. Yeah. So here, which is equal to minus ks theta is equal to j d square theta over dt square, d square theta over dt square plus ks by j theta is equal to 0. Theta is equal to theta naught cos theta cos omega n t, which is equal to theta naught is equal to 0. So we can say that omega n is equal to as a delta of in the radical ks over by j, which is equal to j rad per second. Rad per second is nothing but the SI unit for the angular velocity. So this is the diagram. So j is equal to ks by 4 pi square fn square. So here fn is equal to as the displacement of omega n over 2 pi cycles per second. Okay. When we see that actually the oscillation will gradually die out due to the bearing friction not being 0. If the bearing friction were pure Coulomb friction, it can be shown that the decay envelope of the oscillation is a straight line and the friction has no effect on the frequency. So if the friction is purely viscous, then the decay envelope is an exponential curve, and the frequency of the oscillation does depend on the friction, but the dependence is actually negligible. Well, that means around 0 for the low values of the friction in typical apparatus. So the inertial element. So when we say the inertial element, we'll see real inertia may be impure or have some springiness and friction, but are very close to ideal. So x by f into d is equal to 1 by md squared. That means theta by t into d is equal to 1 by jd squared. Inertial element stores energy as kinetic energy. That means mv squared over 2 or j omega squared over 2. So step input for force applied to a mass initially at rest causes an instantaneous jump in acceleration. That means a ramp change in a velocity and a parabolic change in a position. So the frequency response of the inertial element is obtained from the sinusoidal transfer function, as we have seen in the above, or at the starting point of this section. So the transfer function, the sinusoidal transfer function, can be done or represented as x by f into I omega is equal to 1 by m into omega I omega square, which is equal to 1 by m omega square, which is at the angle of minus 180 degree. At high frequency, the inertial element becomes very difficult to move. So the phase angle shows that the displacement is in direction opposite to the applied force. Okay, so here there is a useful frequency range for a printed model of a real flexible body, and a real flexible body approaches the behavior of the real body if the force is the forcing frequency is small compared to the body's natural frequency. So here the analysis, when we see the analysis, xi minus x naught 2a e over n, that means rho a l x naught rho l square over 2e also, x naught plus x naught, which is equal to xi. That means d square over omega square omega n square plus 1 into x naught, which is equal to xi. That means omega n is equal to, as a delta of in the radical 2e over rho l square. So xi over x naught, that means input to output into d is equal to 1 by d square omega n square plus 1. That means xi over x naught into I omega is equal to 1 by I omega over omega n square plus 1, which is equal to 1 over 1 minus omega over omega n square. So x naught over xi into omega I is equal to 1.05, which is equal to 1 by 1 minus omega max over omega n square. So we can say that omega maximum is equal to 0.218 omega n, which is equal to 0.308 over n in the radical e by rho. That means 96200 cycles per minute for a 6-inch steel rod. So V, that means the velocity, angular velocity, or the omega max, is the highest frequency for which a real body behaves almost like an ideal real body. So the frequency response is unused as a technique for defining the useful and range of the application for all kinds of dynamic system. So the other is the motion transformers. Okay, mechanical system often include mechanisms, okay, such as levers, gears, linkage, cams, chains, and belts. Okay, these are the mechanical system. They all serve a common basic function: the transformation of the motion of an input member into a kinematically related motion of an output member. The actual system may be simplified in many cases to a frictious but dynamically equivalent one. So this is accomplished by referring all the elements that are masses, springs, and dampers, and driving inputs to a single location, which could be the input, the output, or some selected interior point of the system. A single equation can be written for this equivalent system rather than having to write the several equations for the actual system. This process is not necessary, but often speeds the work and reduces the errors. But it's not necessary that it can speeds and it can facilitate the work done. Okay, the motion transformers also you can see these diagrams. These are some the formulas or like this. So this is translational equivalent for a complex system. This is also the diagram for kinematically related things like this. So refer all elements and inputs to the x1 location and define a fixtures equivalent system whose motion will be the same as x1 but will include all the effects in original system. So define a single equivalent spring element which will have the same effect as the three actual springs. Mentally apply the static force, that means F1 at location x1, and write the torque balance equation. So F1 L1 is equal to Ks1 x1 into L1 plus L2 over L1 x1 Ks2 into L2 plus x1 Ks over L1, which is equal to here F1 is equal to Ksc x1. Ksc is equal to delta into Ks1 plus L2 over L1 square Ks2 plus L1 square Ks. So here the equivalent spring constant Ksc refers to the fixtures spring which is installed at location x1 would have exactly the same effect as all the springs together in the actual system. So to find the equivalent damper, here mentally to remove the inertia and the springs and again apply force F1 at x1. So here we can explain or we can represent the formula for this thing. F1 L1 is equal to x1 b1 into L1 plus x2 b2 into L2 plus b theta. So here x1 b1 L1 plus L2 square over L1 x1 b2 plus x1 b over L1. F1 is equal to b naught b naught or bc x1. So here bc is equal to as the delta of b1 plus L2 over L1 square b2 plus L1 by L1 square into b. So finally consider only the inertia present. That means F1 L1 is approximately equal to M1 L1 square into x1 L1 plus M2 L2 square into x1 L1 plus J into x1 L1. So F1 is equal to here we can see that MC x1. So MC is equal to as the delta of M1 plus L2 x1 L2 L1 square M2 plus 1 by L1 square J. Okay, while the definitions of the equivalent spring and the damping constants are approximate due to the assumption of small motions, the equivalent mass has an additional assumption which may be less accurate. We have treated the mass as the point masses. That means J is equal to ml square. Nothing. M is nothing but here M is the mass and L is the length. So we can say that J is equal to ml square. So to refer the driving impulse to the x1 location, we note that a torque T, that torque T is equivalent to a force that means T by L1. T by L1 is nothing but a force at x1. Okay, location, and at the x1 location, and a force F2 is equivalent to a force L2 by L1 times F2. If we set up the differential equation of the motion for this system and solve for the unknown x1, we are guaranteed that this solution will be identical to that for x1 in the actual system. And once we have x1, we can get x2 and or theta immediately, since they are related to x1 by simple proportions. So the other is the rules for calculating the equivalent element without deriving them from scratch. So when referring the translational element, or that means the spring, damper, and the mass are known as the translational elements. So the translational basic elements, the mass, the spring, and the friction or the damper. Okay, these are known as the translational elements. So from the when we referring the translation element, that means spring, damper, and the mass, from the location A to location B, where S motion is n times b. Okay, multiply the elements value by n square. This is also true for the rotational elements. That means coupled by motion transformers such as gears, belts, and chains. When referring the rotational elements to a translational location, multiply the rotational element by 1 by r square, where the relation between the translation x and the rotation theta in the radians is x is equal to r theta. For the reverse procedure, that means the referring translational element to a rotational location, we can multiply the translation element by r square. When referring a force A to get an equivalent force B, multiplied by n, that means holds for torques. Okay, that means multiply a torque at theta by 1 by r to refer it to x as a force. A force at x is multiplied by r to refer it as a torque t theta. That means these rules apply to any mechanism, no matter what it forms, as long as the motions at two locations and our locations are linearly related. So the other is the mechanical impedance. When trying to predict the behavior of an assembling of subsystems from their calculated or measured individual behavior, the impedance methods have advantages. So mechanical impedance is defined as the transfer function, that means either operational or the sinusoidal, in which the force is numerator and the velocity is the denominator in this case. So the inverse of the impedance is called what? The mobility. Okay, the impedance, the inverse for the mobility is impedance, whereas the inverse for impedance is mobility. Okay, the other is the mechanical impedance for the basic elements. These are the diagrams. This is the spring, this is the damper, and this is in case of the inertia. This is the mechanical impedance for the basic elements. So here we can say that ZS, that means the impedance S into D is equal to at the delta of F by V at D, which is equal to Ks by D. So Z at B is equal to it means the impedance, as the first one is impedance in the case of the spring, and the second one is the impedance in the case of damper or the friction element, is equal to ZB into D which is equal to at delta of F by V into D, so which is equal to B only. So Z impedance in the case of M means the mass, so into D is equal to at the delta of F by V into D, which is equal to MD. So measuring the other is the measurement of the impedances of the subsystems. So the subsystems so can be used to analytically predict the behavior of the complete system forms when the subsystems are connected. We can also discover and correct the potential design problems before the subsystems are actually connected. So here the impedance methods also provide the shortcut analysis techniques. When two elements carry the same force, they are said to be connected in the parallel. That means if the two elements carry the same force, and they are said to be connected in parallel, and they are combined impedance in the product of the individual impedance over the sum. Okay. For impedance which have the same velocity, we say they are connected in series, and they are combined impedance in the sum of the individual ones. Okay, consider this following system. This is the series connection of the impedance systems, and this is the parallel connection. Like this. The series means the parallel means parallel only. But when we say the series one after the other, like this is the parallel connection formulas, and this is the series connection formulas. So you have to identify those the parallel connection formulas and the serial one. So here like this we can do, and the force and the motion sources. Here, the ultimate and the real driving agency of any mechanical system is always a force, not the motion. Force causes acceleration. Acceleration does not cause force, but the force causes acceleration, but acceleration cannot. Acceleration does not cause force. The motion does not occur without a force occurring first. The motion does not occur without a force occurring first. Yeah. That means if there is a force, there is what? Motion. If there is no force, there is no any motion. Okay. If there is some, for example, this is one object. This is one object. If I want to move, if I want to move like this, I want what? A force, because I'm applying force from my hand. I'm applying force like this, and then I'm getting some the movement of this object which has mass, and when I apply the force, there is a motion. If there is no any force, it is stored only, right? It is no any motion here. It is the stored thing only, but it's stored but not motion. So if I'm applying the force, there is the motion like this. Okay, this is the concept for this. So at the input of the system, what is known? Force or the motion. If motion is known, then the motion was caused by some or that interacts unknown force, and postulating a problem with the motion input is acceptable. There are only two classes of forces. Forces associated with the physical contact between two bodies, and the action at a distance forces, that is the gravitational, magnetic, and electrostatic forces. And there are no other kinds of forces, which means inertial force is a frictious force. The choice of an input to be applied to a system requires careful consideration, and just as a choice of a suitable model to represent a component or system. Here are some examples of the force and the motion sources. The first example is this: force and motion impulse acting on the multi-story building. So this is one of the example for the force and the motion sources. Okay. Here also a mechanical vibration shaker rotating unbalanced as force input. Like this, they have the examples: electrodynamic vibration shaker as a force source, like this. And here also the mechanical system to be force driven, like this. We can get this diagram: the constant speed drive of angular velocity omega. The force source constructed from a motion source and soft spring is also another example for force source. And the energy consideration, a system can be caused to respond only to by a source supplying some energy to it, and an interchange of the energy must occur between a source and system. If we postulate force source, there will be an associated motion occurs at the force input point. The instantaneous power being transmitted, so this energy port is the product of the instantaneous force and the velocity. Yeah, that means power being transmitted through this energy port is the power is the product of instantaneous force and the velocity. If the force applied by the source and the velocity caused by it are in the same direction, that means power is supplied by the source to the system. So if force and the velocity are the opposite direction, the system returning power to the source. Okay, like this, we have to identify the concepts. The concept of the mechanical impedance is of some help here. The transfer function relating the force and the velocity at the input port part of the system is called the driving point impedance. That means ZDP. ZDP at D into D is equal to FV by D. ZDP at I omega is equal to FV at I omega. This is in the case of the translational, and this is in the case of angular. We can write an expression for power is equal to P is equal to FV. F is nothing but the force, and V is nothing but the velocity. That means F into F by ZdP, which is equal to F square ZdP. So if we apply a force source to the system with a high value of the driving point impedance, not much power will be taken from the source. Since the force produces only a small velocity, the external cause of this with the application of the force to a perfectly rigid wire. A driving point impedance is infinite, since the motion is produced no matter how large force is applied. In this case, the source will not supply any energy. So the higher the driving point impedance, the more real force source behaves like the ideal force source. The lower the driving point impedance, the more real motion source behaves like an ideal motion source. So real sources may be described accurately as combinations of ideal sources and an output impedance characters of the physical device. A complete description of these situations also requires knowledge of two impedances. One is the output impedance of the real source, and the driving point impedance of the driving system. So the other is the mechanical system examples. This is the rack and pinion gear system. Here the other is nothing but the multi-gear system. These are all the examples. Okay, this other is the dynamic vibration absorber. This is also another example. The other is the dynamic rigid body dynamics, or that is known as the kinematics. Reference frames are that means the ground x, y, z, and R1 body body x1, y1, z1. So this is the 3 body diagram. 3D. That means x, y, and z. These are all the formulas. So for any vector q, that means the cross and the cross formula also there here, crossing of the vector. So the rigid body diagram here, the rigid body kinematics example is also like this. We have to see the here in the rigid body kinematics the reference are ground, shaft, and the disc in this area like this. So these are the formulas and the cross product, or after substitution and simplified all you have to find this all you have to derive this all. Okay, rigid body dynamics kinematics or like this. So like this we have to see all of them. So like this we have to find like this. Okay, rigid body kinematics example like this. So like this we have to find all, and these all are very important formulas. We have to see all of the formulas we have to derive, and we have to see all of them. Okay, so from here up to there we have to use this all the dots properties, the cross products of the vectors. All like this you have to solve all of them. Then after that it will be clear for us. Okay. Okay, thank you so much for attending my class. This is the end of our today class. Okay, thank you very much, and I love you, all of you guys. If my video is comfortable for you, please like, share, and subscribe my video, and don't forget to subscribe and to be my family of my channel. So if you have any doubts and suggestion, comment, you can mention in this in the comment place. So thank you for attending my class. Thank you guys. Thank you. Bye bye. Okay.